Okay, if we use s sub x and s sub y for our position, and it probably would have been better to use just x and y, so maybe I'm going to change that here, because I change and use x and y here. We can say that x of t is this and y of t is this. We don't need an extra equal sign, do we? Okay, so Vx is negative 0.8 meters per second, and the position is, we're at the origin of our coordinate system, our x versus y, our y versus x coordinate system, at t equals 0 and Vy equals 0 at that time. We immediately conclude that x of t is negative 8 meters per second times t, and y of t is 1/2 of 0.3 meter per second squared times t squared. We can do integration or any other thing we want to do in order to establish this. And I mentioned this is a correction to what I wrote down last time. I wrote one of these down as a velocity instead of a position. So, generally, if we have zero acceleration in the x direction, which means we have constant velocity, x is going to be Vx times t, y is going to be 1/2 ay times t squared, where Vx is our constant x velocity, ay is our constant y acceleration, because that's what we have, constant acceleration, constant velocity. And of course, again, we make these assumptions about our initial position and time, and velocity. Okay, so our equations then have the form x equals Vx times t, y equals 1/2 a t squared. Can we solve for y as a function of x, eliminating t, to see what the shape of our path is? Because we don't know what the shape of this path is. Somebody might have told you it's a parabola. I probably told you it's a parabola. I know I told you it's a parabola. You might have read that it's a parabola. Do you really understand why it's a parabola? Not that difficult to do. This follows immediately from constant velocity in the x direction, constant acceleration in the y direction, and our assumption of being at the origin at t equals 0 and stationary at that time in the y direction. So to solve for y as a function of x, we'll get a graph of y versus x, and that's going to be a picture of our path. Okay? So how do we do that? Well, we eliminate t. So that's really easy to do. We solve this equation for t and then plug that expression into this equation. When we solve this equation for t, we're going to be solving in terms of x. In other words, we're going to get an x in our result, and then when we plug that in over here, our t is going to have an x in it, and we're not going to have a t anymore. Well, it's easy to see how that happens. Okay, if x equals this, then t equals x over Vx. Then, since y equals 1/2 ay t squared, y is going to equal 1/2 ay times this expression squared, which simplifies very quickly to y is going to be ay over 2vx squared multiplied by x squared. So now we see that y is just a multiple of x squared, meaning that our graph is going to look like this. Okay, y equals some multiple of x squared, and if this is a positive multiple, as it is in this case, we're going to have a parabola with its vertex at its origin. Now, that's a property you should understand from pre-calculus and calculus. If not, kind of review and make sure you understand why this gives you a parabola. For the ay being positive and Vx squared automatically being positive, we know that the parabola opens upward, and we know that since it's just a multiple of x squared, we just stretch or compress our x squared graph, and our vertex remains at the origin. Okay. Now, we are moving in the negative y direction. We were here at t equals 0, and in the negative y direction. Our x motion is this way, and our y motion is going to be this way. So this part of the parabola doesn't have anything to do with our situation. Our situation starts here, and we move along this half of the parabola. And we see then that we have this section of the parabola, we have a parabolic motion. Our direction of motion approaches but never reaches the positive y direction. We talked about that last time. Okay. To get the specific parabola here, well, I went back to the original functions here with the numbers. I didn't use the symbolic solution, but we have to be able to do this symbolic solution because the symbolic solution shows us how things are interrelated, whereas the numbers, it's good to do a numerical solution too because you know what the numbers are for this specific situation. Here, you know what the numbers are for a general, you know how the numbers are going to work for a general situation, but you don't know what the actual numbers are. There are advantages to this and there are advantages to this. Well, if I take this equation and solve for t, I get t equals x over negative 0.8 meters per second. And then if I plug that in for y, 1/2 0.3 meters per second squared t squared, well, I take this expression, replace t with the expression, and I get this. And then I simplify. The square of 0.8 meters per second squared is 0.64 meters squared per second squared. That's going to be in the denominator. We're going to have 1/2 times 0.3 meters per second squared in the numerator, and that's going to be times x squared. And if we work this out numerically, I believe this whole thing comes out to about 0.24 meter reciprocal times x squared. Then we talk about the units of this thing. And are these the right units? You got a reciprocal meter here. Well, what units should we get when we do this calculation? Well, when we do this calculation, we're going to get y. Y is a position, presumably in meters if our units are consistent. So if x is in meters, is that going to give us a y in meters? Well, yeah, because we're going to be squaring the meters of x and multiplying by reciprocal meters, and that's going to give us just plain old meters. So we check the dimension, and then we check this numerical calculation against this symbolic calculation. We plug in our value of AY, we plug in our value of VX, and we see we get exactly the same numbers in exactly the same place that we have here. So we understand by the numbers, we understand by the solution. This y equals 0.24 reciprocal meters times x squared will give us a specific graph for our motion. This is a more general graph that depends on the values of AY and VX.